case, I'm happy to introduce our next speaker, who is Xiao-Wu Chen from USTC, and he will tell us about the homological dimensions of the Jacobson radical.
Thank you. So it's very nice to be here, and thanks for the invitation. So today I will talk about the homological dimension of the Jacobson radical. So please, next page. Yes, so the notation, so this is quite usual. So lambda is always artin algebra, J is Jacobson radical, and lambda 0 is the quotient of lambda modulo the Jacobson radical, so it's semi-simple. And this PD and ID projective dimension, integral dimension, and the global dimension. So please, next page. So recall we have a short exact sequence accurate of bimodules of J include lambda and lambda 0. So it's very well known and classic that the global dimension of lambda is the projective dimension of the lambda 0. So therefore, by dimension shift, then the projective dimension of the Jacobson radical is, in most cases, is the global dimension of lambda minus 1. But in the semi-simple case, you have to be careful. But anyway, we have this well-known formula. So please, next page. So the central result I would like to report in this talk is that with joint work with Srikanth, Iyengar, and Rene Marczinzik, so we prove that we consider the integral dimension instead of projective dimension. In this case, we have a very neat formula. So always that the global dimension of lambda equals the injective dimension on each side of J. So in comparison with the projective side, there we have a minus sign and we have the max, but here everything is quite neat. So just a remark that Rene proved this fact for a certain class of artin algebras in a short paper, but he conjectures after some tests, then conjecture this holds in general. So actually in this paper we prove this actually even more. We prove it for a semi-perfect northern ring. So I can even sketch the proof. So please, next page. Yes. So the key proposition we use that this is kind of formula for projective dimension of a module. So which is a supermom of the non-zero extension between M and the Jacobson radical. So next, maybe yes. Yeah. So clear the next left hand side is bigger. So for other directions, we assume that right hand side is D, which is it's finite. So this non-vanishing. In particular, the extension of D plus 1 of M and J is 0, so that there's this map induced by the projection of lambda to lambda 0 is surjective on the extension. So yes, so thank you. So we have take a minimal project presentation. So then actually you see that each extension of M to lambda 0 is a map from K to lambda 0. So we actually the above surjectivity implies that any map from K to lambda 0 facts through a projective modules. Actually, this proves maybe next. So this proves that K is projective. So this proves that the projective dimension of M is not bigger than D. So we have this proposition. So having the proposition, so next page maybe. So we can prove the theorem. So actually, clearly the global dimension of lambda is bigger than the integral dimension of J. Next. So we know that the global dimension is the projective dimension of the semi-simple module. Then so we use the proposition. We have the equality using this supermom. So sorry, here this M should be lambda 0. Sorry, this is a typo. But anyway, then this is not bigger than the integral dimension of the Jacobson radical. So this completes the proof of the theorem. Yes. So maybe next page. So actually, we try to extend. There's two directions of extension of this theorem. One extension we have to increase the degree of syzygy, because that the Jacobson radical is the first syzygy of the lambda 0. So what about the higher syzygy? So in view of the theorem, we may ask this general question. So if I is bigger than 0, then then for non-zero syzygies, then do we always have the integral dimension of the higher syzygy non-zero is equal to the global dimension of phenomena? So this is the question. I mean, this is quite open. So next. So yeah, can you go next? Yes. So the case I equals 0 is well known. This is given by semi-simple modules. Case I equals 1. This is by the above theorem. And for in commutative algebras, this is true by Gush, Gupa, and Paraka. They prove they have a more general result in commutative algebra. Next. So we answer this question affirmatively for now actually for two classes of algebra. So sorry, this is not updated. But anyway, so we proved that for certain Grunstein algebra and also for minimal or standard Grunstein algebra in the sense of Yama and Swabok, which this by definition is just either is self-injective or Grunstein algebra whose dominant dimension equal to the self-injective dimension. Yeah, so in this, but in general, we don't have a good answer to this problem. So it's looks of interest. Next. Yes, another direction to extend the theorem that we consider the Grunstein analog of the theorem. So that we know that in Grunstein analog that the global dimension is have to somehow be replaced by the self-integral dimension of phenomena. So we consider the Grunstein integral dimension and the Grunstein projective dimension. So the Grunstein analog of the theorem might be we somehow we split the thing into two questions. So do we always have the Grunstein integral dimension of the Jacobson array equal to the integral dimension of phenomena? And do we have the symmetric of integral dimension on each side? Remember that we have for integral dimension we have the symmetry on both sides. We have this they are equal to the global dimension. No, but for Grunstein integral dimension, that's not actually now it's open. So please next. So I mean, why we have some support to why we answer this question. So it's well known that due to Hoshino or also many other people that if we consider Grunstein project dimension of the Jacobson radic on each side, they are the same. And when they are finite, then precisely when this phenomena is Grunstein, so in that case, it's the maximum of integral dimension on both sides. So in the sense that for a Grunstein project dimension, we have this symmetry on each side. Please next. Yes, so recall that this is very famous that the Grunstein symmetric conjecture means states that the self-integral dimension of each side are the same. So actually, we prove that maybe next. Yes, so in the end, we prove that the above two questions are somehow half of this Grunstein symmetric conjecture. We prove that the integral dimension on each side of phenomena are the same if only if these two equation are holds. So namely that the Grunstein integral dimension of J equals the integral dimension of phenomena and also for the opposite algebra. So in particular, these two things holds for commutative algebras. Actually, we proved more for general commutative algebras, commutative rings. So I mean, this is the last slide. I mean, thank you very much. Yeah, thank you. This is all I like to talk about.